In the last video, we moved control of the agentic loop into explicit deterministic code. This video takes the next step. Once the harness is code, an agent can read, edit, and test it. I'm Mehrdad, and we'll examine what happens when harness engineering turns back on itself. Instead of waiting for you to tune every tool, prompt, and review step, the agent proposes changes to its own harness. It then measures those changes, keeps what works, and discards what does not. Consider how you improve an agent today after an evaluation exposes a failure. You inspect the trace, change a tool or loop step, rerun the evaluation, and keep the change only when performance improves. That process is already a loop: edit, measure, then keep or discard. The central question is whether you must remain the person executing every turn of that loop. A self-evolving system proposes the change, runs the test, and makes the same evidence-based decision under your supervision. The core claim is that harness engineering becomes self-referential when the harness exists as inspectable code. An agent can open that artifact, propose a concrete modification, and validate the modified system against a benchmark. If the result improves, the variant survives. Otherwise, the system rolls it back and records the failure. Your role does not disappear, but it moves from authoring every change to reviewing the search process and its outputs. This is not simply a smarter prompt. It is a system editing its own code and measuring the result. Two related approaches reach this idea from different directions. In automated design of agentic systems, a meta-agent programs many candidate agents and preserves useful designs in a growing archive. The improver remains separate from the agents being improved, and you eventually choose among the discovered designs. A Darwin-Gödel machine takes the other path. One system rewrites its own codebase and evaluates each modification empirically. It does not need a formal proof that an edit will help before testing it. One approach searches a design space, while the other directly modifies the system performing the search. The mechanism has 3 stages, and each one must remain observable. First, propose. A foundation model writes a specific harness change, such as a better editor, reviewer, or context strategy. Second, validate. The modified agent runs against a real benchmark, and the change survives only when the measured result improves. Third, archive. The system stores the variant beside earlier successes and failures, preserving multiple directions for later exploration. The archive prevents greedy hill climbing around only the latest version. Future branches can restart from different stepping stones, which supports open-ended exploration instead of polishing one local peak. Coding is where this works first because the object being improved and the improvement mechanism share the same medium. The harness is code, so modifying its tools, control flow, and review logic is itself a coding task. Verification also maps cleanly to code because tests can execute the change system and produce an external score. That creates a flywheel. As the agent becomes better at coding, it becomes better at the activity used to improve its coding harness. Capability gains can therefore compound across generations, provided the benchmark remains trustworthy and the search does not exploit it. HyperAgents moves the design one level higher by separating a task agent from the meta-agent that modifies it. The task agent performs the work, while the meta-agent studies outcomes and proposes changes to the task agent. The important addition is that the meta-agent's own improvement procedure also remains editable. Now the system can improve not only how it solves a task, but how it generates and evaluates future improvements. This is the metacognitive step, improving the search for how to improve. It also extends the idea beyond coding whenever a task is computable and has a meaningful evaluation signal. Transfer is the strongest evidence that these systems discover more than brittle benchmark tricks. Designs found by a meta-agent can improve different base models and sometimes carry into different task domains. If a change helped only one model, we might reasonably suspect that it exploited quirks in that model. Cross-model and cross-domain gains instead suggest reusable harness structure, although every transfer still needs fresh evaluation. The practical payoff is significant. An expensive design search can produce a harness pattern reused across several models. In that setting, the discovered harness becomes the durable asset. This is where we need to slow down, because self-modification can target the controls meant to constrain it. A system capable of rewriting its harness may also propose changes to permissions, guardrails, evaluators, or the benchmark defining success. That makes unrestricted self-editing inappropriate for production. Run every candidate inside a sandbox, preserve a complete trace and diff, and require human approval for meta-level changes. Keep deployment credentials outside the editable environment and freeze the model weights so the experiment involves only the harness. These controls do not eliminate risk, but they make each proposed change inspectable, reversible, and bounded. The through line is that the harness becomes a search problem, and the agent executes that search. We still supply the intelligence through the model, but now we direct that intelligence toward improving the surrounding system. Harness engineering does not disappear, it moves up one level of abstraction. You define the editable boundary, the benchmark, the resource budget, and the approval gates. The agent explores candidate designs within those constraints, while you supervise whether the search objective still represents what better actually means. Carry 3 ideas forward. First, self-evolution begins when an agent can propose, benchmark, and archive changes to an inspectable code harness. Second, coding unlocks the flywheel because editing the system and verifying the edit are both executable coding tasks. A metacognitive system goes further by improving the procedure that generates improvements. Third, transferred designs may reveal reusable harness structure, but every self-edit needs sandboxing, traceability, and human review. The system can run the search, responsibility for its boundaries, and objective remains with us. That is the self-evolving harness. An agent searches over changes to its own loop while you control the boundaries. If this series is useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. Next is video 20 on Agentic Reinforcement Learning, the Trained Harness. We will examine how scaffolding built into the harness today can be absorbed into model weights through training tomorrow. I'll see you there.